I dropped it on the ground. If you could imagine that. We'll see. The green light's on. There we go. The rate is the velocity, so that's 3, and the time is 4 seconds. So we can say we know the total distance traveled is 12. Do you agree with me on that? Whatever units happen to be on there. What if I graphed this problem on where x is the time axis and the y-axis is the velocity? Notice I only put 4 marks because the seconds are from 0 to 4. And if the velocity is a constant velocity of 3 whatever, you agree that that would just look like a line like this, like it's a constant velocity? And if I stopped that at 4 seconds, could I kind of draw a line in here to say I'm kind of bounding that in from 0 to 4 seconds? Do you agree that that's kind of what that would look like? So this is, your book says this. I didn't come up with a sentence, but it made me laugh. It says, now suppose you are Isaac Newton trying to make a connection between the distance formula and the graph of the velocity function that we got over there. Notice anything? This is a lovely little rectangle, right? Where this is a length of 4, this is the length of 3. If I found the area of this little shape that I made from 0 to 4 seconds with a constant velocity, the area ends up giving me the same answer that I got when I did the distance formula. And so the next slide here, you don't have to write all this down, but I just kind of trying to put it together here for you, and then we're going to look at a couple other problems today. But this is not, I think the words that the book says is, this is not a coincidence that this happens.
So does that only work after it's started to work?
No. Oh, this is no accident, it says. Since the distance traveled and the area in this case are both found by multiplying the rate 3 by the change in time 4, this same connection between distance traveled and the area could be made no matter how fast, I put the train, apparently I didn't write about the train in this, was going, or how long or short the time interval was. So it could be from 1 to 2 seconds, and that would just change your shape, right? But the formula would still be the same, because now you would just be for 1 second, but this height would still be 3. So it doesn't matter if it doesn't start at 0. But the big issue is, what if the velocity was not constant, right? What if the velocity was a formula like 7x squared? Then that's not going to make a geometric shape. That region under the graph would no longer be rectangular or any other geometric shape that we could use. And so that's where the calculus part comes in. To save the day, I wrote that part myself. Today is going to be like kind of baby steps into calculus and some geometry. The big idea for these first couple sections is that if you can make a geometric shape and they ask you to find the distance traveled, if you can make an area that you can use the formula, a triangle, a rectangle, a trapezoid, we can forget that one, a circle, if that's the shape, then you can just do the area formula. But if it's not a geometric shape, like this, right, and I just wrote, I'm just going to put from A to B here. What if that line was my velocity graph? And what if from A to B was my time interval? And I said, I want to find the area of that, or the distance traveled, which I know is area. Anybody have any suggestions of how we could estimate the distance there instead of getting the exact distance, maybe? Because that's not a geometric shape we know, right? Don't write on this on your paper yet, because I can hit undo. One thing, what if I just drew a line here for this rectangle, would that give me somewhat of an estimate if I made one big rectangle out of it? Yeah. What if I broke it up into more than one rectangle? What if I broke it up like this into two rectangles and I said, let's cut off like this one here and this one here? That one's a little bit underestimating, that one's a little bit overestimating. Would that be more accurate of an estimate than just doing one big rectangle? What if I broke it up into even more rectangles? What if I broke it up? Those are equally spaced. What if I broke it up 4 rectangles and I made it like this, like here, here, and here, and here? Do you think that would be more accurate if I broke it up into more rectangles? What if I broke it up into, let's say, hypothetically speaking, 100 rectangles? Would 100 rectangles leave less space there to be inaccurate? Or what if the number of rectangles was eventually approaching infinity? What do you think would happen? It would be like the same exact area, right? That's where we're going with this. Not today, but that's where we're going with this. And so today when they talk about breaking things up into rectangles, it's because, hey, I'm going to get a pretty accurate representation, and do I know how to find the area of a rectangle pretty easily? Yeah. And so we're not going to actually call it this today. I'm going to go ahead and tell you that your book, if you look in your book today, because we're only doing one part of this section, they call it RAM, which stands for Rectangle Approximation Method, or Rectangular Approximation Method. RAM is another name for another thing we're going to call it later, but we're going to make a program for RAM, and it's really cool because instead of you having to break this up into 100 rectangles, we can use the calculator and tell the calculator to break it up into 100 rectangles, which is much easier than me telling you to make 100 rectangles and find the area of each one, right? Right. All right, but today we're going to make like 4 rectangles, and we can do that by hand. All right, so that's where we're going with this. And area formulas. That's kind of, so how can we find the distance? Let's say rectangles. You do only have 4 problems on your homework today. 2 of them involve just geometry formulas. 2 of them involve this estimation because it won't be a constant function. How do you know the difference between them? Well, you got to look at what they give you for the velocity. So this one says a particle starts at x equals 0 and moves along with a velocity v of t equals 3t for t greater than or equal to 0. Where is the particle at t equals 3? What's the new distance? How far did it go? That's another way to say it. So let's just kind of graph this just like our other one. This is going to be my t-axis. This is going to be my velocity that I'm graphing here. And we're only going for 3 seconds, and so don't make a million lines. Oh, so it's going to read how many seconds here we're going. So I'm just going to go 1, 2, 3. And you can graph this however you want. That's just a linear function. Do you agree with that? So if you want, you could just graph the y-intercept and a slope of 3 over 1, or you could just plug in numbers like at 0. You agree I'm at 0, and at 1 I'm at 3. I like to think the biggest I'm going to be. At 3 I would be at 9. Do you agree with that? So I need to go to 9 on my y-axis, or label by however you want. Label by 3 if you want to. At 1 I'm at 3. At 2 I'm at 6. 3 at 9. And it's linear, which means it's a constant velocity there. Constant rate, I guess. Constant acceleration. And again, something that we're kind of not used to doing is stopping. We're stopping at 3 seconds. We're talking about how far did it go, but we're trying to relate that to area. So I always like close my figure in. If I'm stopping at 3 seconds, I'm going to draw this line down to 3 seconds so I can look at this and say, hey, is that a shape I know how to take the area of? Hey, it's a triangle. So how do we find the area of a triangle? times height. And so the big idea here is that if you can find the area using the velocity function and the time it traveled, that area will be the same as if you just found the distance. So the area is base times height. And the nice thing is you have a graph so you can see that the base is 3 units long and the height is 9 units long. And that would be 27 halves. Whatever, 13 and a half. I have to say, during the test yesterday, I was taking the AP exam that was released in October, the 2014 exam, and I did the whole no calculator multiple choice part, and I missed 6 questions, and I'm so mad because 2 of them were stupid mistakes. Like, one of them I had the answer, and then I circled this answer, and I like had the answer right here, and then I circled the wrong one, and I was so mad. Stupid, I wrote next to it. And then another one, I tried to solve an equation like this, and I said this. And I did the whole problem, and I was like, how? My answer is not up there. And so I just guessed, and then I went, like, I always finish them all, and then I grade it, and then I come back, and I try to fix the ones I did wrong without knowing what the right answer is. And then I was like, all right, I'm just going to restart the whole thing, because I had to do something wrong. And then when I got to this again, I was like, I'm so stupid. So mad. So I'm really only counting 4 wrongs, right? Like, I really missed 6, but 4 legit wrongs. 2 stupid mistakes. But it reminded me, because there's some fraction stuff like this, and on the multiple choice, no calculator, they always leave as fractions, because you don't have a calculator, and fractions are easier to keep than decimals, I think. But it's okay if you write 13 and a half. Here's the big issue. As we start into this rectangle stuff, which is what we're going to do next on the next example, people forget about this. They forget that you can just do area. So anytime from this point forward that they talk about where has the particle ended, what is the distance traveled, if the shape is an area, you can just do area. Every year on the AP exam, there are questions that they just want you to break it up into geometric shapes, and every year people forget that, and they try to do way more complicated stuff. And so we start with this, and we'll continue seeing it here and there, but I'd just like to remind you that this is a great way to do a problem when it's a geometric shape. What about this? Aren't you allowed to print these out? This one, same idea. Particle starts at x equals 0 and moves along the x-axis with a velocity. So now look at our velocity. Our velocity is 2t squared for time greater than or equals 0. Where is the particle at? T equals 3. And we'll just skip the other stuff right now for a minute. But the issue is, the reason that they have to tell us this after the question is we're not going to be able to find the exact area of this, because when we graph this velocity, it is going to be a curve. It's not going to be a geometric shape that we can find the exact area of, so we're going to have to estimate the area. And right now, to do that, we're going to make rectangles. How do we know where to make our rectangles? That's what this part means. So let's make the graph first. Again, we're only going to 3 seconds, so I'm going to make mine kind of spread out here so that we can see our rectangles. 1, 2, 3. You want to kind of be somewhat equal spaced. If I plug 3 in here, I'm going to get 18 as my highest value. Do you agree with that? So I'm just going to make my y-axis go by 3s just because I don't want to make 18 marks, but whatever you want to do. We should know the graph of this is a parabola. I'm going to make a decent graph right now just because I want you to get to see these rectangles. Eventually, you won't necessarily even have to make the entire graph every time to do this, but on this one I want to. So if I plug in 0, if I plug in 1, I get 2. Right here. And if I plug in 2, 4 times 2 is 8. Maybe like here-ish. And if I plug in 3, I get 18. And it's going to just be this nice curve up, sort of like that. Yes? and then I'm going to drop it down to 3 seconds. And then it says use 3 rectangles of equal width. If I'm going for 3 seconds and I want the rectangles to have equal width, does it make sense that for this problem I could just draw in some lines like this and that makes 1, 2, 3, like each one is 1 unit long? 3 rectangles, so that means width of 1 apiece. Does that make sense? If it said 6 rectangles, then I'd break each one of those in half again, right? So you just have to make them equal spaces. My line's off a little bit. But how do I know how high to make them? And they tell me it, all right? 3 rectangles of equal width, got that part. And heights determined by the midpoint of the interval, all right? By the midpoint of the interval. So I'm going to change colors here just so you can see. I know it's hard for you to do this in yours. But from 0 to 1, do you agree the midpoint would be 1/2? The height of that rectangle is going to be where is the function at 1/2. And I'm just going to go up here and say that is going to be the height of my rectangle. And notice what happens. This side of the rectangle is going to be a little bit above my line, but this side is going to be a little bit below. So that first rectangle's height is going to be whatever the y value is at 1/2, which I'm just going to estimate right now. So they tell you what to use as the height of the rectangle, because otherwise all our answers are going to be different. If we don't use the same height, then your estimate's going to be different than my estimate. I mean, close still, but we want to get used to doing it which way they tell us to. So the same thing on this. If I went right here in the middle between 1 and 2, that would be 1 1/2, or I'm an improper fraction fan, I'm going to say 3/2. And I'm going to go up to the function and say, where does the velocity hit at 3/2? And it would be roughly about right there. And I'm going to draw in that second rectangle. And again, notice, part of it's above the line, part of it's below. So using the midpoint seems like a decent thing to do because maybe it kind of averages out the overestimate and underestimate on each side. And what would be between 2 and 3? Don't say 2.5. 5. And go up here and just kind of estimate it. And it would be sort of, you can tell my graph is not perfect here, but like this. Yeah. Could we find the area of each one of those rectangles and add them together to get an estimation of this? Yeah. So we want to find the area of the 3 rectangles. We like rectangles because it's an easy formula. Length times width, or base times height, or I don't know, how you want to think about it. The length of this is just 1. Do you agree with me on that? So the first rectangle I'm going to say is 1 times the height. How would I find what the height is? Like, how tall is that first little rectangle? When x is 1/2, where could I plug 1/2 in to get what the y value is for that right there? Could I plug 1/2 in here to get what that is? So I'm going to show that on mine. I'm going to say I'm going to do v of 1/2 to get the height. So this is my base, or my length, I don't know. This is my height. Do you agree the height is actually on the velocity function? So it comes from the velocity function? This is where calculators are super great because your calculator will do fractions for you, and you're going to get really good at typing this stuff in your calculator. And so it's great to practice that. So again, if you didn't bring your graph calculator today, bring it tomorrow because I want you to start using it as opposed to the scientific one. And I'm going to go ahead and just do all of them, okay? The second one is also a base of 1 or a width of 1. But the height is now, what is the y value when I plug 3/2 in? So I'm going to do v of 3/2. And if you want to go ahead and say 2 times 3/2 squared, right? I'm okay with that. I'm just trying to show you where it comes from on my paper. And the last rectangle is also a base of 1. But now the height is, what is the y value when I plug 5/2 in? So I'm going to say v of 5 halves. Really, fractions like this would always be probably on a calculator portion of the test. If they were decent numbers, they could give you something like this on a no calculator. There has been some decent arithmetic on the calculator, no calculator portion of the test. But these are just ones, so I really don't even need the ones there. But this is just going to be 2 times 1 half squared plus 2 times 3 halves squared plus 2 times 5 halves squared. And you can really type that all in your calculator at once. And you can hit the math fraction, decimal to fraction button, and it'll give you the, if it's a crazy improper fraction, we get some weird answers sometimes. This one might not be. But get used to doing that. If you don't want to do it all at once, don't do it all at once, but you need to get used to using your calculator because we're going to be typing in a lot of estimations like this. This one isn't terrible because it is fractions, or halves, but. So that's 1 half plus 9 halves plus 25 halves. So 35 halves, is that right? Did I do that right? Yes, no? My brain's not a brain. Math 1. You need to learn that button. Love that button. Yeah. And you can really, I'm typing all this at once in my calculator just to remind myself that it does work. Yeah, well that means you got one from a previous year, which is perfect, because I'll get faster when we sort it around. Is 17 and a half the exact area of this? No, but it's a decent estimate. If I made more rectangles, do you think it would be a more accurate estimate? Which is why RAM, using the program in our calculator, is great because we can plug in really big numbers for how many rectangles we want to do. And then that kind of leads us into, well, how could I find the exact area? And that's the calculus part that we're not getting to yet. So here we go, I got one more. Let's do the same thing, but now let's do 6 rectangles instead of 3 rectangles. So I'm going to show you something here, and then you can decide whether you like it or not. You don't necessarily have to draw the entire picture every time, all right? Because what you really need, think about when we're doing this, and we'll write this out more tomorrow when we do it. What you really need is you just need to know what are you plugging in for your velocity each time, right? And you need to know how long your intervals are. So when I do this, especially as I do this over and over again, drawing the entire picture every time is not so much fun for me. So what I do is I draw the x-axis or the t-axis, and I say, okay, from 0, 1, 2, 3. Let's figure out how could I get 6 rectangles, what would the widths be, and then what would be the numbers I'm plugging in to find my height. All right, so last time we did 3 rectangles, it was just 1, 2, 3. So if I want 6, do you agree I'm just going to cut each one of these in half? So that would be 1 half, 3 halves, 5 halves. And if you want to draw the whole thing, draw the whole thing. I'm just trying to save you a little bit of time. Because you can see, look, I'll even just draw some here. It's going to look something like that, because it's going to have that, I think it actually starts down here, right, going up like that. But I have 1, 2, 3, 4, 5, 6 rectangles. Everybody with me on that? What is the width of each one of those rectangles? How wide is each one of these? 1 half. So my width or my base or my length, I don't know what you call it. I always call it the width. The width on this one is 1 half for each one. Yes? No? Any clue what I'm saying? The height, that's the important part. You have to figure out what value are you plugging into that velocity function for t to find it. And it's the same as number 2, which means we want to use the midpoint of each interval. So you need to go through and figure out what are you using as a midpoint. And in this case, between 0 and 1/2, you agree that's 1/4? And then if you just count the 1/2 as 2/4, right? Just count by fourths. This is 1/4, 2/4. So halfway between 1/2 and 1 is 3/4, 4/4, 5/4, 6/4. This becomes 7/4, 8/4, 9/4, 10/4, 11/4. The worst part is when you do your numbers wrong because you just make a mistake. It's happened. I always check and make sure it makes sense that 11/4 is less than 3, so I did it right. So you see how you don't actually have to draw all the rectangles in? You can if you want. You'll actually see that the amount of white spaces are like over and under is much smaller. But the formula for each rectangle is going to be 1/2 times plugging in all 6 of those into that, right? So I'm going to say 1/2 times 2 times 1/4 squared plus, okay, I'll stop for a second. 1/2 times 2 times 3/4 squared plus 1/2 times 2 times 5/4 squared plus 1/2 times 2 times 7/4 squared plus 1/2 times 2 times 9/4 squared plus 1/2 times 2 times 11/4 squared. And again, it's up to you on how much you type in your calculator. If you do it all at once, the nice thing is check the odd ones in the back and make sure that you get the same answer that they did. The answer to number 2 and number 3 should be somewhat similar. So if we get way off answers, then we did one of these wrong. Couple things to notice about this. Since the widths are all equal widths, could you factor the 1/2 out front and just have 1/2 in front and then all the stuff in the middle? You can do that. This one, it kind of makes no sense to do that because why for it?
Because the 1/2
Yeah, 1/2 times 2 is just 1. So I wouldn't do that on this one either. But if the width was like 7/2, maybe we want to, maybe not. So cancel out. But I agree. I agree for it. 1/2 times 2 on each one of these is just going to be 1. So I'm just going to get 1/16 plus 9/16 plus 25/16 plus 49/16 plus 81/16 plus 121/16. When you're using these methods, I need to see some work in there. You don't have to show me every step. If you show me like this first step and then you have an answer, that first step shows me you set it up right. So you got to make sure that you show me the setup in there. I think showing a little bit of work is even better because if it's an open-ended question, you can get points for it. A lot of times, every year on the AP exam on the free response, there'll be a question asking you to set up some sort of sum like this. There's lots of ways we can do it besides this. But you get points for the setup. So if you don't show the setup and you only show the answer, you don't get points for that. Anybody got an answer yet? Sorry, I'm just doing mine too. 25, 16. I shouldn't have my notes out. I'm just winging it today, kids. I'm so excited. 16 plus 1 over 16 plus 121 over 16. Yeah, okay, we'll do both. So I got 17.875. Is that what you said, Philip? Oh, 143 over 8. When you're comparing answers, 143 over 8 compared to 27 over 2, maybe you struggle doing that, which is why looking at the decimal, comparing 17.5 to 17.875, those are pretty close answers to say, oh yeah, those are probably pretty good estimates. If we broke it into 12 rectangles, you think we'd get even closer to the right answer? 100 would be way closer. So that's kind of where we're going with this. Tomorrow we will look at actually talking about RAM, and there's 3 ways we can do RAM and using the program on our calculator. So please make sure you bring your calculator tomorrow, or you're not going to end up with the program that you need to do your homework on. Okay? So time 1, day 1, you're just doing 1 through 4 all. I believe 2 of them have geometric formulas and 2 of them are using the rectangles. I think one of them ends up being a trapezoid maybe. In case you don't know the area of a trapezoid, well, one, you could just draw the height down and you can make it 2 rectangles and or a rectangle and 2 triangles. But area of a trapezoid shows up a lot. I think it's worth knowing that the area of a trapezoid is 1/2 times the height times the sum of the bases. We'll talk about that many times over the year or this semester, but it's a good one to write down, and it's a good one that when you see a trapezoid that you can do it. Usually our trapezoids are on their sides, meaning that the height is usually the base, and then like it's anyway. We'll talk about it. Let me see it. Look at me, are you prepared for the final sheet?
Haven't had one of these before.
Happened to wait a whole day of testing yesterday. Okay. Look at that. We survived even